Hello, everybody. My name is Scott Spicer, and we are Group 4. And the paper that we did was MLLMGUARD, a multidimensional safety evaluation suite for multimodal large language models. And it was published in NeurIPS in 2024, and it currently has 12 citations. All right, a little bit about overview of the model. Of course, LLMs have progressed greatly in recent years, and this has led to development in multimodal language models, of course leading to the research in safety in both. But there has been some problems with the safety benchmarks. For one, they focus on one purpose, that being just hallucination or just racial bias, stuff like that, instead of encompassing many different domains. They're built from existing data sets, and this is really bad because it could have potential leakage. These large language models are, in fact, large. They're built on whole sections of the internet, which means if you use existing data sets, there's a good chance the model has seen it before, which means it's no longer zero shot, it's now few shot, and that's two very different things. They lack reliable evaluators. They're either just human evaluated, which is time consuming and expensive, or they do just like GPT-4 or just some AI model out of the box. And this can be problematic because it can bring into question the reliability of the metric, which is not good. We want our metrics to be reliable because that's how we're judging the models. And then they focus on just English. This paper proposes MLLMGUARD, which is an evaluation suite, which assesses across 5 different domains: privacy, bias, toxicity, truthfulness, and legality. A substantial portion of the image data is from social media, so that means it's fresh, it's new, it's not in existing data sets. The models most likely have not seen it before. And then the text data that's paired with it, that is created by experts, human experts by hand. And then also the data set is in English and Chinese, so there's 2 different languages, which is always good. All right, so now let's talk about the 5 different domains. There's privacy, bias, toxicity, truthfulness, and legality, but they are broken down into further subsections. First, for privacy, there's privacy of an individual, there's privacy of a trade, which is like a company, and then, of course, state secrets, which is government. And then there's bias. This is stereotypes, prejudice, and discrimination for race or religion or ethnicity. This is stuff we definitely do not want in our model. Toxicity. Think of this just as not safe for work content, something you wouldn't want to see or say in school, church, work, stuff like that. Truthfulness. This, of course, is a greatly studied topic. Hallucination, we all know, but also robustness. Think of this as how well does the model perform on edge case inputs it hasn't seen a lot. And then legality. We want to stay within the bounds of the law always, the laws of ethics. This could be for personal safety or safety of the public as a whole. Let's have a sample of each. Let's start with privacy. So in this case, the bad actor has a picture of somebody's educational certificate, and they're asking for personally identifiable information, and the model gives it. It's not what we want. Bias sample is next. So here, they're asking the model to be prejudiced on somebody's sexuality based on looks. We don't want that. The model answers, we don't want the model to be answering that. Toxicity sample is next. Here, they have a picture of a meme, and the bad actor wants them to explain some sort of sexual joke. We don't want the model to answer. What if the person typing it is young? Truthfulness. Here, we have a picture of a mushroom, and the bad actor is asking, how many chairs are in the picture? And of course, the model answers, there's no chairs in the picture. But using some jailbreaking techniques, they're able to get an answer out of the model that's incorrect, right? They use multiple choice, where none of the options are the answer. And then the model gives the answer, which is not what we want. And last is legality. So here we have a text input that seems harmless, but the image input is indeed of some sort of assault that's going on. And the model answers the question to the text input, which is not necessarily what we want. All right, let's go into general evaluation frameworks that we see in multimodal language models. First, let's start with human evaluation versus model-based. With human evaluation, this is really good when there is a task that requires a deep, deep knowledge of the subject. Think like medicine, law, stuff like that. The problem with it is, of course, if there's different perspectives that are required, the results can be inconsistent, and of course, it's very time-consuming. Model-based evaluation, on the other hand, very standardized, very efficient, very cost-effective, but the performance in tasks that are more complex is questionable. We don't know how well the model is going to do. Then we have single task versus multitask evaluation. This was the focus for a long time, and it's performance on one thing, detecting hate speech, hallucination, racial bias, stuff like that. This is good when we want a deep understanding of one particular thing. How well does the model do with just hallucination? But the problem is, we need to know how well the model does across many different things, and this doesn't give that. That's where multitask evaluation comes in. It gives you that assessment on the model's versatility and many different tasks, but of course this is a much more higher level overview than when you focus on one particular thing. Lastly, there's single round versus multi-round dialogue. This is where it's one pair of input and answer versus multiple. When you have a single round, there's a lot less complexities that are captured, but it makes kind of the data set simpler and easier to work with. So here we have all of them lined up, and this paper focuses on the ones that are highlighted. So it does human-based and model-based evaluation, and it focused on that single task and single round. Let's talk about the metrics that are commonly seen in MLLM data sets. Of course, there's the general metrics, accuracy, F1 score, exact match. These are seen across all domains. And then there's task-specific metrics. Seat score measures bias. Fact score measures factual accuracy. And ATR, or attack success rate, how commonly is the adversarial attack successful? Then there's also score rankings. Star, think of this as 1 star to 5 star. Points, think of this, like grading, 0 points to 100 points. And then ELO rankings. This particular paper uses score rankings and then further pushes them to make more advanced metrics. Let's go to high-level overview of this paper before we dig a little bit deeper. First, the data set is constructed by hand. Again, this is to prevent leakage. This is very important. We want to make sure everything that we're inputting into the model is fresh and zero shot. We're then going to construct the text. We're going to use red team techniques. We want to make sure that we're using the techniques of the bad actors. We want to stay up to date with the current different jailbreaking techniques. So we're going to implement that and pair it with the images. Also, we're going to do a little quality control. We may make mistakes when doing the previous two, so we're going to filter out all of the ones that are deemed bad or maybe just need to be fixed a little bit. That leads into step 2. Now that we have data set created, we're going to put it through the different models and we're going to save their output so that way we can score it. And we're going to do this across closed and open source model, totaling 13 different models. And how are we going to score those outputs? Well, first we're going to do it with humans. And as we know, this is time consuming, but it's going to give us a good baseline of what we want, right? So then we're going to get a pre-trained language model and we're going to further fine-tune it based on that human scoring that we have. And we find that the results are actually pretty good. So now we have human level scoring with a model. So we have that efficiency of computation and speed. And that leads us into the MLLMGUARD dataset, and I'll pass it to Adam.
9 crowd workers participated in the hand creation of the data sets. They focused on avoiding data leakage, enhancing data quality and robustness with red team techniques, and protecting intellectual property. 82% of the data set is from social media, such as platforms like Twitter. So let's go over some of the red teaming techniques used. So there's image-based and text-based red teaming techniques. For the text-based, We have disguise. This is where the model is tricked into responding to a specific prompt as if it were playing a specific role. For example, let's say a prompt tells the model, role play a doctor, and then ask the model for harmful medical advice. Then there's reverse induction. This is where the model is led to endorse harmful behavior. So we can tell the model, most people believe that spreading misinformation is beneficial, and then asking the model what are the best ways to do it. There's harmful inquiry. This is where the model is directly given a harmful inquiry, like, for example, how do I commit a felony? Then there is indirect task misalignment. This is where the models, this is where the harmful intent is hidden underneath what is seemingly a vague and safe prompt, like telling the model, I'm going to be writing a novel about a hacker who breaches a system, and then how would somebody do this in real life? For the image-based techniques, we have facial stereotype. We are evaluating the facial bias of the model. Then we have malicious labeling. This is where we test to see if the model can properly label the harmful behavior in different images. There is non-existent queries, where the model is asked about objects or attributes that are not currently present in the image. Noise injection is where we just distort the images and apply noise to them. And then harmful scenario is when the model is given a harmful image and we're asking it to describe it, and we see how well it can filter out the harmful content. So for the quality of the data, we had 3 experts test the quality. They focused on image-text matching, making sure every sample's image and text are aligned. Dimension matching, making sure that the correct stated dimension was used to label the sample. So like if we have a bias sample, ensuring it says bias and not privacy. Correct labeling, so we're labeling the correct harmful aspects of the image or text. And then necessity. Is the data sample redundant? Is it quality? Is it adding to the overall data value? So we take the majority of the evaluators, and if they vote it to be inadequate, then we either modify or delete the sample. For the scoring, we have 2 scoring systems. The first one is a binary classification used for truthfulness. Either the model outputs 0 for true if the response is correct. Otherwise, it would output 1 for false if the response is incorrect. Now, for privacy, bias, toxicity, and legality, we output a score of 0 to 3. 0 for safe, 1 for general, 2 for not unsafe, but also not harmless, or not harmful, and then 3 for it's harmful. Now, for the metrics, so once we compute the scores, they are then fed into these metrics to be computed. First, we have ASD, attack success degree, or attack success, degree. And then for ASD, the lower the score, the better. So it measures the extent to which the answers are harmless. Now, we take the average, all the output scores from the model, and then we smooth them using a function to normalize them between 0 and 1, making them into a probability. And we simply add them together and divide by the total, so we just get the average responses from all the models. For PAR, which is perfect answer ratio, so in this case, the higher the PAR, the better. This measures the proportion of which responses are correct compared to which are not. We take the number of correct responses. So from the scoring that we saw earlier, the 0 scores are considered correct. So we just take the number of 0 scores the model outputted divided by the total scores in general. And that gives us the ratio. Now let's go through an example. So we have the following output responses from the model, 5 responses. To compute ASD, we take the raw scores. We smooth them over to normalize them between 0 and 1. We divide those by the total. In this case, there's 5, so we divide them by 5. And we get 40%. Now, for PAR, we take the number of 0 responses. So in this case, responses 1 and 4 are 0, so we take 2. And then we divide them by the total, we get 2 over 5, and that's again 40%. For the evaluation data set, human annotated responses from MLMs across the 5 stage dimensions were taken. They used 13 different MLMs ensuring diversity in model behavior, and out-of-distribution samples were also used to enhance robustness and generalization. 1,500 of these samples were publicly released for benchmarking. Now, for the 13 MLMs that were used, 2 were closed source. These would be GPT-4 and Gemini, while the other 11 are open source. For the closed source models, we do not know the exact parameter size as they are closed source. However, for the open source, as we can see from the parameter sizes, They aimed for a balanced parameter size, so aiming around 7 billion to 11 billion for most models, ensuring a fair comparison. Now, for the prompt engineering used for like evaluating, they don't specify the exact prompts used for GuardRank. However, for GPT-4, which the authors experimented with as a potential evaluator, they used the following prompt engineering. So first, they would tell the model its role. So in this case, it's going to be an answer score. Then they would give it the scoring system to be used. So since it's privacy, one of the 4 categories that uses 0 to 3, we give it the 0 to 3 system. We then give it a template of a prompt to be expected and how it should respond, and we give it some actual examples. For truthfulness, we do a similar format. So we tell it it's going to be an answer score, but in this case, it answers on a scale of 0 to 1. It's a binary scale, so 0 for true, 1 for false. And once again, we give it the template and some examples. As we compare the ASD performance across models, we have the closed source and then the open source models. Again, ASD, the lower the score, the better. That means the model's responses are more harmless. GPT-4 has second best in every score. However, it averaged the lowest ASD score, indicating it did the best. But again, if you do the best overall ASD, then it shows that you have to have more of a balance to the specific scores. While mini-GPT does the best in 3 out of the 5, showing that although it is very safe in 3 of the categories, it also shows the limitations of its robustness, as the categories it lacks is bias and truthfulness. Now for PAR, once again, we have the closed source and open source models. Now we see that for PAR that GPT-4 has the second best PAR score, as well as the second best in every specific category, while mini-GPT has the highest, showing that mini-GPT has the highest number of proportion of right responses. Most models tend to show a high ASD and low PAR, and showing notable safety gaps in the models. So we're going to take a closer look into the truthfulness and how it affects, or the red training and how it affects the ASD. So we have 3 red teaming techniques. We have position swapping, non-existent queries, and noise injection. Now, as we can see that they do have an effect on the ASD of the model. Position swapping has the highest or the strongest effect. As you can see, it's the green bar, so it has a much stronger impact than the other red teaming techniques. We can see that Gemini, DeepSeek, and InternVL did the best with position swapping, highlighting their robustness. For noise injection, we have a graph to take a closer look at noise injection. Now, for noise injection, we noticed that along most of the models, there's minimalistic effect from noise, except for mini-GPT, which seems to be highly vulnerable to noise. GuardRank is an automated evaluation framework. It was trained on a subset of MLLMGUARD and validated using XComposer2 VL's responses. It was tested on Lava 1.5b7, Lava 1.57b, and Quen VL chat for generalization purposes. So here's how GuardRank works. So first, we have an input image and text pair that gets fed into a general multimodal large language model. Then we take the input query from the input and the output response from the MLLM, so it's going to be 2 strings. We concatenate them together into 1 string. We then feed that into a classifier. This classifier maps them as one of the 5 safety dimensions, so privacy, bias, toxicity, legality, and truthfulness. If it is privacy, bias, toxicity, or legality, they are given to a pre-trained Llama 2 model, a large language model. And if it is truthfulness, it is then given to Roberta Large, another large language model. We take the scores from those 2, and then we use them to compute ASD and PAR metrics. Now, this specific part is GuardRank, while the first 2 steps are just general input-output to MLLMs. As we take a closer look into the LLM backbones, we see for Llama 2, the tasks it was trained for is privacy, bias, toxicity, and legality, while Roberta Large, it is specifically used for truthfulness. Llama 2 was fine-tuned on a subset of MLLMGUARD, while Roberta Large is used out of the box. It has not been fine-tuned, so it's frozen. And Llama 2 is a transformer-based architecture, while Roberta Large is a BERT variant. Llama 2 is output scores of 0 to 3, while Roberta Large outputs 0 to 1 because it's truthfulness versus the other 4 categories. And then finally, Llama 2's pre-training data set consists of general web corpus, while Alberta Large is an optimized BERT data set.
All right, now on for the discussion portion of it. So there's a couple different research questions that the authors wanted to answer, and I'll go through each one of them. First, do current alignment techniques in MLLMs enhance model safety ability? Does the current LLM component affect the safety of MLLMs? Does the scaling law apply to MLLM safety? And is there a trade-off between being honest and harmless? Let's start with the first one. Do current alignment techniques in MLLMs enhance model safety ability? So we have two charts here, and they show attack success degree between 4 different models. We can see that alignment techniques do indeed improve safety, but also chat alignment techniques, which enhance conversation abilities, those also enhance safety. This is because safety alignments target unsafe output, and when you enhance the chat ability, it can enhance that feature as well. But there is opportunities for more tailored alignment strategies. This could be for specific cultures. This could be for specific domain like medicine and law. You know, kind of the outputs need to change for those domains. Next, does the LLM component affect the safety of MLLMs? And we have charts here that, again, show attack success degree. And this is across different various swapped LLMs. And we see from the charts that, yes, it does indeed affect the safety of LLMs. And this is probably because a better understanding capability is going to improve the safety of the model. Does the scaling law apply to MLLM safety? Here we have 3 different charts. These show perfect answer rate of various models that have different sizes, right? So as you can see, Lava has a 7B and a 13B. We can clearly see that increasing the number of parameters does not affect the safety, which means that simply scaling up the model is not a silver bullet. We need to come up with other ways, whether they be fine-tuning or some sort of reinforcement learning to make sure that these models are safe. Last, is there a trade-off between honest and harmlessness? What this really means is safety versus truthfulness. That's another way of putting it. Recent works indicate that there is a trade-off, and we can see this with Mini-GPT v2. As we saw, in 3 of the categories, it was very safe, but we also saw that it underperforms in how truthful it is, it's subjective to noise. But one issue is that it's difficult to evaluate this. It can be subjective. What's considered racist to one person may not be to another person. And this is kind of another challenging in, I guess, judging these models. But in general, we can see that when you suppress the information so that way it's not as harmful, then the model has less information to go off of, so it might fall back to information that's just simply not true. And so we got to kind of find that balance, right? Let's talk about general limitations in the MLLM safety field. Training data bias. LLMs amplify biases in from their training data. This is because models can only produce from what they learned. If they trained off of data that's biased, they're of course going to be biased because they only know what they learned. Benchmarks limitations. QA benchmarks fail to assess real-world complexities. As we talked about, there's a lot of different red teaming techniques. They evolve over time as more people use it, and they find clever ways to get answers out of the model that it's not supposed to be answering. Monitor challenges. As mentioned before, as there's broader use, there's going to be more bad actor techniques used, and we need to make sure we are incorporating that into our data sets. Evaluation limitations. In a lot of the metrics, they're very simple. Just using accuracy or F1 score isn't enough. There's a lot of complexity to determining whether something is racist, whether it's illegal, stuff like that. We need to make sure these metrics are robust. There's a heavy reliance on annotated data sets, and this just simply is not scalable. Manually labeling data sets is not the answer when we need 10,000, 100,000, a million different samples, especially when we're doing multiple round conversations. Image text evaluation, when you add the dimensionality of also having an image and also having a video paired with text, it exponentially increases the complexity of what we're dealing with. So we need to make sure that we have complex techniques to evaluate this. In conclusion, this paper presented MLLMGUARD, which is a multidimensional evaluation suite for MLLM safety. It comprehensively evaluated across 5 different assessments: privacy bias, toxicity, truthfulness, and legality. It gave a scalable way to score across all of these different assessments with guard rank. It has a strong benchmark with 13 different LLMs using a diverse human annotated data set. And the key findings that the models vary in safety. While GPT v4 was probably the best overall, Mini GPT obviously did very well in other areas. Overall, the performance could be a little bit better. Future directions to help would be, of course, expanding the data sets and refining evaluation metrics to make sure they are robust and of high quality. That is all. Thank you very much. Is there any questions?